Hello and welcome to another video. This video is about integration by parts, one of the very useful techniques you would use in integration. And sometimes you have more than one option of the technique to use in taking an integral, the same thing you would experience when you're taking derivatives, but sometimes there's only one way to do it. And that's the case in the case of integration by parts. Sometimes you may be able to do some U substitution or some smart trig substitutions, but at the end of the day, there are some functions that you just have to use integration by parts. Now, what does this mean? Well, this is from the product rule. So this is, you can call it the product rule of integration. Remember the product rule in differentiation? This is just a rearrangement of the product rule. Let me show you. I want you to recall that if u is a function of x, okay, and v is a function of x, just imagine. And then you multiply these two functions together, giving you uv. If you try to take the derivative of this function, do you remember what you're going to get? Well, the derivative of this product from the product rule in differentiation is keep the first, differentiate the second. Keep the first, differentiate the second, plus differentiate the first, keep the second. I'm sure this is very plain, very easy. Okay, what if we rearrange this piece so that this one goes over here? If this goes over here, it becomes uv quantity prime minus u prime v. So we're going to have u v prime equals uv quantity prime minus u prime v. That's it. See, this is beginning to look a lot like this. What happens? If we want to recover our uv, well, we have to take the integral of every term. See what happens. If you integrate the derivative of a function, well, you get the function back. That's the fundamental theorem of calculus. Actually, that's how we got into integration. So this is going to give you straight uv. Well, not all of this is integrated, or differentiated, so we just have to leave it that way. It's u, or you can rearrange it as v times u prime. So it looks like what I've got there. So it's going to be v times u prime, and on this side it's going to be the integral of u times v prime, and that's what this is. So this is very easy to remember. You just want to know that whatever function you're given to integrate, you must judge the original function you're given to integrate as having a composition of a function and the derivative of a function. Well, we're going to take some examples and you will understand it, and you'll be able to integrate many functions that you would otherwise not be able to integrate. Let's get into it. Okay, so let's take this first example, the integral of sine x cosine x dx. Integration by parts, because you're multiplying two terms, will be the first thought for someone who so much loves this. But you can also see that you can use u substitution because the derivative of one is the other, at least a form of the other, and the derivative of one is the form of the other. So you can actually use u substitution, and that's what I'm going to show you, that you will still get the same answer depending on the method you use and which one is faster for you. So let me show you. So using u substitution, so I'm going to say let u be equal to sine x. So that tells me that du will be equal to sine x dx. Okay. I'm sorry, will be cosine x. Do that again. du will be equal to cosine x dx. But what you notice is that cosine x dx is right here. So I can actually rewrite this expression and say that the integral of sine x cosine x dx is equal to, when I do my u substitution, well, remember I said u is sine x, will be the integral of u, and then what is cosine x dx? Well, that's du. What? That's what u substitution does, but that's not the focus of today, okay? So this is going to be, if you take the integral of u, well, it's going to be 1/2 of u squared plus c. Well, we're done. What is u? Well, we said u was sine x. So we can easily go back and say it's 1/2 of sine x squared, which is sine squared x plus c. This is what you will get if you did u substitution. So I'm going to leave this on this side, and then we're going to say, assuming it wasn't this easy, or you were so much in love with integration by parts that you decided to do it, what should we do? Well, we're going to use the formula for the first time in this video. I love it. Okay, so now when you see a function, let's write it here. The integral of sine x cosine x dx. You have to ask yourself, which of these two parts can I easily differentiate, and which of them can I easily integrate? You must ask those two questions, because the one you can easily integrate will be the one that you call dv, so that you can integrate it. The one you can easily differentiate is the one you're going to call u, so that you can easily differentiate it. Do you see how you think? So you must choose wisely. But fortunately for this question, we know how to take the derivative of sine x, or even cosine x. We know how to integrate sine x, or how to integrate cosine x. So whichever you choose will give you the same answer. Now you may have to do some more extra work if you don't choose wisely, but you'll still arrive at the same answer. But I do recommend in this case to just make your u to be sine x and make your dv to be cosine x. So let's go. So we're going to say, let u be sine x. I want you to arrange it this way and immediately write du. What will du be? Well, du will be cosine x, just like we did here. Okay, now, see, I'm leaving out the whole dx that is attached to it. We're going to put that back just to make our work clean. Let's go here. We're going to say dv, so arrange it this way. Just the way the question is, dv is cosine x. What is v? Well, if you integrate cosine, what would you get? You're going to get sine, okay? Sine x. Now let's just plug in the formula, okay? So the formula says u dv, which is the problem that we have, because if you look at it, the integral of u dv will be u dv. So we can say the integral of sine x cosine x dx is equal to uv. Look at that, uv. That's sine x times sine x. That's sine squared x minus an integral. And what's the integral? It's going to be v du, which is v du. That is sine x cosine x. What? Sine x cosine x. Okay, we just put the dx there, okay? We have to put the dx every time you take an integral. Now, or maybe I should just put it in front of it so you can see. So this is dx, and this is dx. Okay, so that makes it better. But one thing you've observed is that the question, the problem is a part of the solution. And that makes your work come to an end. So remember, every time you write something like this using the integration by parts formula, and you notice that what you have on the right hand side looks exactly like what you have on the left, or is a form of it, a multiple of it, okay? You're done. So just move this over to the side and add it to the original problem, and you're going to end up with 2 times the integral of sine x cosine x dx will be sine squared x. See how beautiful that is? So what is the solution to this problem? It's going to be that the integral of sine x cosine x dx, well, divide everything by 2, you're going to get 1/2 of sine squared x. Does it look like this? Yep. Plus c. Now, I showed you that you don't have to use integration by parts. Okay? You can use u substitution when you know it works. So for u substitution, you have to be able to see the future. For integration by parts, you have to be able to see the present and see that you can integrate one and you can differentiate one. That's all you've got to do. Okay, before I move on to the second question, which is this one, let me explain to you why in some cases it doesn't matter which one you take as your u and which one you take as dv. Because in some cases, if you switch them, you will never get the answer because things get more and more complicated. But in the case of sine and cosine, you notice that when you differentiate one, you get the other. When you integrate one, you get the other, okay? Maybe with a plus or a minus, whatever, but that can be taken care of, okay? But we're talking about the quantity. So, do they alternate? Yeah, if they alternate, it doesn't matter which one you take. You might have to do extra work to get the answer. But in some cases, if they don't alternate, you want to look for the one that goes to 0 the more you differentiate it. Remember, integrating makes things more complex because it gets bigger and bigger. That's the meaning of integration. You're summing things up. But differentiation, you're narrowing things down, so you're likely to get a 0. So when you have a polynomial, in this case, you don't want to integrate a polynomial. You want to differentiate a polynomial because the power will become gradually, will reduce gradually until it gets to 0, no matter how many times you have to do it. Okay, but when you have this, because they alternate, I'm sure you can switch them. So let's just try out making u cosine x and dv sine x and see what kind of answer we're going to get. Okay, so let's do it. So we say let u be equal to cosine x, and we have du will be equal to negative sine x. So we have dv equals sine x, and then we're going to have v will be equal to negative cosine x. So let's use our formula. The integration of sine x cosine x dx, which will be our u dv, will be equal to uv, u times v will be negative cosine squared x, minus the integral of v du, which is negative cosine x times negative sine x, which is going to be sine x cosine x. I just put the dx back there. Okay, now what do we have? Well, it looks like this is the same as this, so we can move this over here, and we're going to have 2 of the integral of sine x cosine x dx. So remember, you will always have situations like this where what you have at the beginning, just like we had at the beginning there, what you have here will be the same thing as this, so it doesn't matter, okay? And then we're going to have sine x cosine x dx will be equal to negative cosine squared x. So our answer says it is sine x cosine x dx. So this will be negative 1/2 cosine squared x. Well, it looks like we didn't get the same answer as we got the first time using u substitution, and right here using u substitution, and when we said u was equal to sine x. But wait, remember, we can do the Pythagorean substitution and transform cosine into sine, and let's see what's going to happen. Remember, our answer in this case was equal to 1/2 sine squared x plus c. Remember, this c was a constant, we don't know what c is. C could be anything. Because remember, when you take the derivative of anything like this, the c disappears, whether it's 1 or 2 or -5 or whatever. Okay, so let's do the transformation of this. Remember, this would be the same thing as -1/2 times, this is 1 minus sine squared theta, 1 minus sine squared x, rather, sine squared x. Okay, now what do you see? -1/2 multiplies that, so your answer becomes, and this multiplying this gives you positive sine squared, so it would be 1/2 sine squared x and minus 1/2. Well, this will be the C or the D or whatever you care, and nobody cares about this at this stage, because what's important is the function that you get, not the constant, because the constant can be anything. Remember that. So what's important is you can just rewrite this as equal to as 1/2 sine squared x plus, let's just call it D this time, since we already use C for this case, but it's the same thing. I can still call it my C, actually. I'm just going to call it C. So you see that when these two alternate, when you have sine and cosine and it's alternating, you can take it as your integral or your derivative, depending on what the other companion is. And I'm going to see if I can find another example to use this. So remember, integration by parts, in the case of these alternating trig functions, you can actually choose either as the derivative, as the derivative